Have you ever wondered what it is like to go at the speed of light? What are the fundamental building blocks that make up the universe? Imagine you wanted to understand how a car works. You could take it apart and examine the engine, the wheels, and every tiny component. But you can't do that with particles like electrons or protons. They're far too small to open up or look inside. So instead, physicists use particle accelerators to study the atoms and particles that make up our universe. They accelerate particles to incredible speeds very close to the speed of light and smash them together. Almost like crashing two cars to see how they're built, except these cars are smaller than an atom. There are two main geometries of particle accelerators. Linear accelerators, like the European XFEL in Germany, accelerate particles along a straight path. Circular accelerators, like synchrotrons, send particles around huge rings before colliding them, just like the Large Hadron Collider at CERN. Let's see how a particle accelerator works using a ball-bearing accelerator. This is a solenoid coil, and this is a magnetic ball. In this accelerator, the solenoid coil represents a single accelerating structure, while the magnetic ball represents a bunch of electrons. When current flows through the coil, a magnetic field is created with a north and a south pole. If the ball enters the coil with the opposite magnetic pole facing the coil, it is attracted and accelerated. By placing many accelerating structures in a straight line, particles get a small boost of energy at each stage. Together, this forms a linear accelerator, allowing very high energies to be reached. The same idea can also be used in a circular accelerator, where particles pass through the same structures again and again, gaining energy with each pass. Now let's design this ball-bearing accelerator. To accelerate our magnetic steel ball on the circular track, we use an IR sensor and a copper solenoid coil to synchronize the ball's arrival time with the accelerating field. This process is controlled using an Arduino UNO microcontroller board. The setup needs two DC power sources, one to power the IR sensor circuit and the other to supply the voltage and current to generate the magnetic field. Let's put our particle accelerator to the test. Our tabletop model contains 6 sensor coil pairs connected to the Arduino board. Each sensor detects the ball as it approaches, and the Arduino triggers the corresponding coil with a carefully timed pulse. By knowing the distance between the sensor and the coil and estimating the ball's speed, we can choose the delay so that the magnetic field acts mainly in the forward direction. In an ideal case, each coil would give the ball a small push, and the ball would gain speed as it moves around the track. In practice, several effects oppose the motion. The ball loses energy due to friction with the track and air resistance. Its motion is also affected by small misalignments, spinning, and wiggling, which can change how efficiently the magnetic force accelerates it. So, how does this relate to real particle accelerators? In our ball-bearing accelerator, the magnetic field provides the push. In real particle accelerators, RF cavities use oscillating electromagnetic fields that give charged particles a small boost each time they pass through. Thank you for watching. To explore even more advanced particle accelerators, visit our website. And stay curious.